All right, let's get started here. So, Monika, you're all set?
Yes, yeah.
Cool. Hello. It's a pleasure to introduce Monika Schleier-Smith as today's Vamos speaker. So as a fellow founder of Vamos, Monika is no stranger to the virtual community that we have here, but perhaps there are some things you don't know about her. After receiving her undergraduate degree from Harvard in chemistry, physics, and mathematics, forgive me if I've forgotten any, Monika. She then went on to pursue her PhD at MIT with Lon Bulatich. There, as a Hertz Fellow, she performed groundbreaking research that opened a field that continues to thrive today, that uses cavity-mediated interactions to prepare entangled states that enhance our ability to perform measurements. She then moved to Germany for a postdoc at MPQ before she was quickly hired by Stanford. As a PI, she's continued her work in quantum metrology and has also explored connections to many-body physics, quantum information, and even quantum gravity, both theoretically and experimentally. Her work has been recognized with numerous prizes, only a subset of which includes the Robbie Prize, a Presidential Early Career Award, an NSF Career Award, an AFOSR Young Investigator Award, and most recently a MacArthur Fellowship. She's also a great colleague and fellow Reading buddy. Thanks for being with us today, Monika. One thing. As a reminder, you can submit questions in the Zoom Q&A or the YouTube chat. And there will be a post-Vamos discussion, as usual, with Monika and a Zoom link that I'll post just at the end of the talk. Okay, go ahead, Monika.
Thanks so much for the invitation to sort of be on the other side of Vamos today as a speaker. The title of my talk is Atoms Interlinked by Light, Programmable Interactions and Emergent Geometry. And it's a talk about some work we are doing on using light to control interactions between laser-cooled atoms. And for this audience, I perhaps don't even need to remind you that laser-cooled atoms are wonderful tools for quantum science. But just to sort of briefly review, right, we have actually over the past few years, there have been extraordinary advances in terms of the ability to have both single atom control and detection, and a high degree of scalability, where it's possible to really take individual atoms and look at them one by one at the level of sort of hundreds of these. So these are, that's sort of one aspect of our toolbox that we're rightly sort of proud of in the AMO community. And at the same time, and this actually sort of is a starting point for applications in a number of different directions, ranging from using the atoms for extraordinarily precise measurements of time in atomic clocks, to building up quantum gates towards the goal of ultimately having these individual atoms be the elements of a quantum computer. Or in the nearer term, perhaps short of universal quantum computation, there is already been extraordinary work in the direction of harnessing these systems for simulation of particular problems that naturally map onto the systems we can build in the lab. So that might be letting the atoms encode spins in the magnetic material and using the system to, in a tunable way, explore properties of some artificial magnetic material rather than needing to grow a different material in the lab to see what the phase diagram will be. So all of these are kind of directions that are powerful applications of cold atom systems, and particularly for these last two of computation and simulation, one sort of other essential feature of the toolbox is the ability to have a high degree of control over the interactions between the atoms and the ability to engineer entangled states. And there as well, there are a number of sort of existing capabilities that allow us to explore these directions. So for example, I've shown here a couple of pictures of interactions coming about by collisions, so direct contact interactions among atoms in an optical lattice that give rise, let's say in this case, to antiferromagnetic ordering, or longer range interactions between atoms realized by coupling them to Rydberg states. That allows, for example, for realizing a picture that looks very similar, some sort of checkerboard ordering of atom in a ground state, atom in an excited state coming about, again, from sort of nearest neighbor interactions between atoms that are individually trapped in tweezers separated on the micron scale. And that type of approach has even given rise to highly entangled states. So not just ordering of let's say, atoms spin up, spin down, spin up, spin down, but macroscopic superpositions of every other atom in the up state, every other atom in the down state, but one doesn't know which is in which state. So that's some highly entangled state, all of which is realized in this case by just local interactions between atoms, either directly colliding or having longer range van der Waals interactions on the micron scale. So I want to kind of emphasize that one limitation, though, if these systems is in fact that atoms so far in these examples I gave only interact with their neighbors. In order to sort of take this toolbox one step further, we would love to be able to go beyond this kind of local connectivity. So just to give an intuition for why you might want to go beyond local connectivity, let me give sort of an example from the classical world, right? So a classical example is the internet. The internet gives us non-local connectivity, and that's something that I certainly got to know very well over the course of many VAMOS seminars over the past year and a half, where I actually spent much more time interacting with Adam and Shimon as co-moderators than talking to my next door neighbor. And that was really sort of transformative in the way I learned about kind of, the latest developments in AMO physics. So what matters somehow these days is not sort of who is your next door neighbor, but who can you access by some non-local connectivity over the internet. So that's really important for the flow of information, even classically. But in quantum systems, connectivity likewise matters, the connectivity of interactions. So just to give a couple of examples, if I have a system of, let's say, spins with nearest neighbor interactions on a lattice, or qubits with nearest neighbor interactions on a lattice, that is a natural way of making a state called a cluster state that is a resource for universal quantum computation. If I had the same sort of type of interaction, but every atom talks to every other, this all-to-all connectivity turns out to be a natural way of making a state known as a squeeze state that is a resource for enhancing clocks and sensors. If I have all-to-all connectivity but some randomness in the connectivity, not equal strength between all atoms, that turns out to be actually potentially a good starting point for having information that is initially locally encoded in one quantum bit very rapidly spread across the entire system, become, so to speak, scrambled, hidden in complex correlations and entanglement among all atoms. And that is actually potentially a model for what happens to information that falls into a black hole. It's not lost, but it's very quickly scrambled. And lastly, if you have a sufficient degree of kind of not just random interactions, but some ability to program the graph of interactions, that could be a good way of taking some real-world problem in optimization, let's say, and mapping it to the problem of finding the minimum energy configuration of a system of interacting spins. And so that could be a route towards harnessing these systems for computation. So kind of the key points here are that the structure of the interactions governs the form of entanglement, and also potentially the capabilities of the system for computation. So one would love to have the ability to kind of, in a versatile way, control the graph of interactions in these systems. So just to give kind of one concrete example, I thought I would zoom in a little bit on this case of optimization. And that's something that you might read about actually sort of on the internet, or if you read the news, you'll find companies that are claiming that they're going to solve your scheduling or logistics problems, help optimize the returns on your financial portfolio, or even optimize fleet operations for holiday deliveries. So there are, lots of questions about, first of all, can quantum systems actually help with these issues? Is there a speed up? Does entanglement play a role? What role would entanglement play? But I always read these things and wondered, how do you sort of take a real world problem and actually encode it in a physical system? So here's one example of a real world problem, which is that I have a bunch of objects with specified weights, and I want to know whether I can separate them into two groups that would balance a scale. And so, for example, these might be my groceries. I want to put them into two bags that I can carry in a balanced way. And actually, for certain configurations of the weights and the number of objects, this is actually an NP-complete problem. There's no efficient classical solution. As a physicist, if I wanted to try to solve this problem, one thing I might do is to try to map it onto some kind of a spin problem. So I could, for example, define the imbalance between these two grocery bags as, well, I'll think of sort of an object in the green bag as a spin pointing one way, an object in the white bag as a spin pointing the other way. And let's say let's call those plus n minus z. And I could write down some imbalance that's the sum of the weight times the z component of the spin, and I want that to be 0. So I could minimize the imbalance, or equivalently, I could minimize the squared imbalance. And that would actually look like some sum of products of these spin operators. So there'll be an energy cost if the spins are, so the energy will depend on whether the spins are aligned or anti-aligned. And so that looks like some kind of a interacting spin system, and the couplings between the spins depend on the weights of the objects, right? And so if I want to sort of encode a particular problem, I need to be able to program the couplings between these spins. So I'd like to have some way of encoding a spin, some way of having non-local interactions among the spins, and some programmability of those interactions. Okay, so the physical system that we use in our lab in order to have non-local interactions is we trap atoms in an optical cavity that lets photons basically convey information between distant atoms. So photons can allow any atom to talk to any other. And our goal is going to be able to have some programmability of the structure of those interactions by controlling a laser field that drives the system. So before I get into programming the structure, let's just sort of let me give you a flavor of actually how it is that photons can mediate interactions between atoms. And the simplest case is if I have two-level atoms, I'll call the two states spin up and spin down. What I can do is I can have a process where an atom flips its spin by emitting a photon, and that photon gets absorbed by another atom, and this generates some kind of a spin exchange process that's mediated by the light. Now, you might worry about sort of whether the photon will actually be absorbed by the other atom or fly off into free space. And to ensure that it's with high probability absorbed by the other atom, that's why we actually put a resonator around the system, and that enhances the probability that an emitted photon will interact again with other atoms in the system. So that general concept of photon-mediated interactions is applied actually in lots of platforms, not just atomic systems, but also microwave photons mediating interactions between superconducting qubits, optical photons mediating interactions between solid-state spins. Or I've shown here a few different examples in the sort of cold atom world, where one sort of thing to highlight is actually kind of the scalability of this general principle. So there are experiments done, let's say, in the group of Gerhard Rempe, where photons are used to mediate interactions between two atoms, realizing a quantum gate. Or at an opposite extreme, photons can be used to mediate interactions within ensembles of hundreds of thousands of atoms. And in this kind of many atom regime, one of the big directions that has been explored is using the ability to have many atoms talk to each other via a single mode of light as a way to generate collective entangled states. So to generate a highly symmetric form of entanglement, which can manifest, for example, in squeezing the quantum noise of the state. So here's an illustration of a situation where one starts with a spin polarized state. It's shown as some kind of a Gaussian blob of the collective spin because there are quantum fluctuations in where it points coming from quantum projection noise. And by having photons mediate interactions among these atomic spins, it's possible to generate correlations that reduce those fluctuations in a particular quadrature and allow you to build, for example, a more precise atomic clock. And so that's been explored in a number of experiments and recently pushed to enhance the precision of in optical clock atoms, even as in this example shown here. So that's kind of one direction where photon-mediated interactions have a strong track record already of generating entanglement in systems of up to hundreds of thousands of atoms. A second direction where there's already a variety of research going on is harnessing these interactions in the area of quantum simulation. Just to give a couple of examples, photon-mediated interactions have been harnessed to study supersolidity in the group of Tillman-Esslinger, or in the group of Ben Lev to actually use the photons in an optical cavity to kind of mimic phonons in a solid-state system that can interact in the same way that phonons can mediate interactions between electrons. The photons can mediate interactions between the atoms, forming a sort of a compliant optical lattice that actually responds to the motion of the atoms and gives you the equivalent of sound waves in a crystal. So those are some directions that are already explored, and quite broadly to sort of expand what's possible, both in terms of what entangled states one can make, and also what phenomena one can simulate. We would like to have sort of, to push forward the programmability of the interactions that we can generate. And if we can do that, we can take this toolbox in some new directions. So a few directions that have been proposed include kind of motivated by solid state systems, studying the physics of spin glasses, or perhaps motivated by quantum gravity, realizing some exotic toy models that are hard to realize with any sort of form of local interaction, but could be realized with this toolbox of photons and atoms. So what would we like to sort of program? Quite generally, sort of there are a few different knobs we might like to have. So one that I mentioned is the graph of interactions. And I kind of showed here a few different directions that we had kind of been motivated by theoretically in terms of having control over the graph of interactions. Maybe we'd like to control the sign of the interaction, should the spins align or anti-align. And you might also want to control the form of the coupling. So do we have these Ising interactions that I showed earlier in one example of an optimization problem, where the Z components of the spins want to align or anti-align, or perhaps some flip-flop interaction where these spin exchange processes that I showed you how you might make, which equivalently I can think of as the spins wanting to align or anti-align in the X direction. So for this talk, I'm actually going to, these are all directions we've explored in terms of programmability of the interactions. I'm going to be focusing on control of the spatial structure and also the sign of the interaction in the case of these flip-flop type interactions, which I can equivalently think of as an XY type of a model. Okay, so the physical system where we do this is one where we have essentially an array of little clouds of atoms trapped in an optical resonator. So just to give a flavor, this resonator is essentially two mirrors separated by 5 centimeters. And we have a lens below so that we can image and trap and manipulate the atoms with light that goes through this lens. And the kind of figure of merit for the coherence of the interactions, we said we want an atom that emits a photon. We want that photon with high probability to go into the resonator and not into free space. That sort of ratio of probabilities for the photon to go into the resonator as opposed to flying off in a random direction is parameterized by what's known as the cooperativity, which in our system for a single atom is 5. But we work with little clouds of many atoms, which gives us an additional boost of this figure of merit. And in particular, in our system, we actually have 10,000 atoms per site in this array. The scale of the whole array is it's about 1 millimeter long, so we have these little clouds of atoms spaced by about 50 microns. Okay, and motionally the atoms we can think of as kind of pinned. Our physics is done with the atoms actually additionally confined in the 1D lattice along the cavity axis, and all of the dynamics will be going on in the spin degrees of freedom. Okay, and so specifically, I showed you before sort of conceptually how you can realize a spin exchange interaction mediated by the light. And we'd like to do it in a way that is optically controlled. So actually our 2 spin states are going to be 2 ground Zeeman states. And if we want to turn on an interaction, we'll turn on a control field that drives a Raman process where an atom absorbs a photon from the control field and can flip its spin and put a photon into the cavity. That will be a virtual process that's not resonant, but the resonant process will be pairwise spin flips corresponding to the interactions that we want to realize. Okay. Now, sort of to add one more layer to this, in our experiment, actually, I gave you sort of a cartoon picture where states are spin up and spin down. But in our experiment, we have 3-level atoms. This is the F = 1 ground state of rubidium. And one of the ways we like to probe the system is by starting with all of the atoms in the 0 state and letting photons mediate a process where 2 0 atoms turn into a +1 -1 pair. And generically, there's no reason why the left or the right atom should be in the plus or the -1 state. So this ought to be kind of a mechanism for generating kind of correlated atom pairs, a superposition of -1 +1 or +1 -1. Okay, we probe this in this array of little clouds of atoms. So what does that look like? So here's an experiment where we start with all atoms in the 0 state. And we do, let's say, 30 repetitions of the same experiment where we turn on light and after some time measure how many atoms are in each of the -1, the 0, and the +1 state. So in this figure, the 3 columns represent the 3 internal states. And then within each column, you can see a little one-dimensional array that represents the individual sites of our array of ensembles. So the kind of the more yellow means there are more atoms in this particular site and in the 0 state, let's say. Okay, and the different rows are different shots of the experiment. And sort of one thing you'll notice is that, first of all, there are kind of large fluctuations in terms of how many atoms are in the 0 state versus plus or minus 1. But the populations in plus and minus 1 are always correlated. So there are these large and correlated fluctuations in populations. And these correlations are a signature of this pair creation process where 2 0 atoms give rise to a +1 and a -1 atom together. One of the things that you'll notice is that the correlations kind of extend across the entire cloud, right? So when there are more atoms in -1, there are more atoms in +1, and that's true across the entire cloud. And that's kind of a signature of the fact that any atom can talk to any other. These atoms are coupled to the single mode of light, and the spatial position plays so far no role in these dynamics. And in fact, actually, the system is quite well modeled. People sometimes ask, like, how do you model this system? Sort of microscopically, it's this flip-flop type interaction. But kind of because the spatial position plays no role, we can really think of this system of spin 1 atoms as essentially 3 bosonic modes. So I could call them the A mode, that's the -1 atoms, the B mode, that's the +1 atoms, the C mode, that's the 0 atoms. And we just have this process that allows you to destroy two 0 atoms and create a +1, -1 pair. And it turns out if one kind of does a couple of coordinate transformations, you can think of this system as equivalent to 2 harmonic oscillators, but one with negative mass and one that's sort of an inverted harmonic oscillator. So 2 unstable oscillators. So you can actually think of these dynamics as there's an instability to kind of rolling down a hill that corresponds to creating these correlated atom pairs. And so sort of as a function of time, I showed you measurements at a fixed time, but as a function of time, there's exponential growth in the population in the +1 and -1 states until some saturation occurs. So that's kind of and this is, again, so the system so far is well described as just kind of these essentially 3 bosonic modes with no spatial structure. And it's very similar to what one sees if one actually has direct collisional interactions in a Bose-Einstein condensate. There, the symmetry comes from the symmetry of the BEC. For us, it's the symmetric coupling of the atoms to the cavity. So this is very similar to actually collisional interactions that have been used to generate highly entangled twin Fock states, where you know you have exactly the same number of atoms in +1 and -1, but have no idea which state any atom is in. Or also a form of squeeze state in this spin 1 system known as a spin nematic squeeze state. So in the context of direct collisional interactions, this is kind of well established as a tool for generating entanglement with applications to quantum sensing. And one direction that we're interested in exploring is, first of all, directly measuring, can we show entanglement generated by these cavity-mediated pair creation, and harness that perhaps for some quantum-enhanced sensing. But beyond that, what we're particularly interested in is the fact that because these interactions are occurring over kind of millimeter length scales, we ought to be able to go beyond this kind of single mode picture and start to control something about the structure of the interactions and hence the structure of the entangled states that one could prepare in this system. And so that's the direction that I want to go. So far, we had every atom talking to every other via this single mode of light. And what we'd really like to do is start to program the graph of interactions. So that's where I'm headed. But before I get into that, I'm going to pause and ask whether there are any questions on what I've said so far.
Yeah, we got a few questions here. So the first question is just stepping back in the context of using these kinds of systems for optimization problems, like number partitioning. Is there a sort of like a clear idea or established notion of like how many qubits we would need in order to outperform classical algorithms?
Yeah. That is a great question, and I don't have a simple answer to it. I think so. The first thing I'll say is, as a starting point, just being able to explore even in small systems this question of kind of how do you use the quantum system, and what role, if any, does entanglement play in finding a solution. There are lots of kind of open questions to explore even before one gets to the point where there's an advantage. Then the other thing that I'll maybe say about this is that for many of these problems, there are, not surprisingly, heuristic classical algorithms that work pretty well. So for example, maybe there's a classical algorithm that's not guaranteed to find the absolute best solution, but it finds a pretty good solution, right? And so, being able to sort of compare to the quantum system, you really have to kind of establish what exactly is it you're trying to do. Are you trying to find the absolute best? Is pretty good enough? So all of these are kind of, I think, things one has to consider in making the comparison. But I would say in the near term, just being able to explore what the quantum systems do and compare different approaches, which I'll maybe touch on a little bit later, is already something that, just from a fundamental scientific standpoint, is to me kind of the exciting question in the near term.
Yeah, definitely. Okay, and then another question is, so for the ensembles at each site, so like in the picture that you have here, should one think of each ensemble as like a continuous large spin degree of freedom that's coupled under this spin model, or rather is the correct picture that you have a spin model of individual spin 1 particles, where at each site you have multiple of these spin 1 qubits or qubits?
Yeah. So microscopically, we have individual spin 1 particles, and when I kind of wrote down a Hamiltonian here that we'll start to play with more later, I'm kind of thinking of these little f operators as representing individual spin 1 atoms. But to the extent that the couplings are the same, let's say for all atoms on a given site, or in what I showed you before, essentially for all atoms in the cavity, then I can kind of symmetrize over that system where all the couplings are the same and think of it as a collective object. It turns out that for this pair creation physics, it's not quite enough to think of it as just a large spin, because, for example, in the case I showed you, we start with the total spin being kind of 0 on average, right? Each atom is in this m equals 0 state. And so kind of sometimes for certain cases, if I started in a spin polarized state, I would find it useful to think of it as kind of a large spin. Here it's a little bit different, and we're going to kind of, when we model the system, we actually think of it as kind of 3 bosonic modes, the sort of -1, 0, and +1 mode on each site. But within each site, we think of the system as kind of being symmetric. So microscopically, you can always think of it in terms of individual spins, but often there's kind of in terms of calculating what we expect the dynamics to be, or thinking about what observables we actually measure, there's some collective observable on the site that's what's going to be relevant to us.
Got it. And I guess related to this notion of being able to treat all of the atoms within an ensemble equally, or perhaps the atoms within different ensembles equally, what is the role of the temperature of the trapped ensembles? Like, what is it, and how does that influence the physics that you're looking at?
Yeah. We work with a trap depth, just to give a sense of scale, that's kind of a few megahertz. Kind of a couple hundred microkelvin, and the temperature is actually sort of a substantial fraction of the trap depth. So it's maybe half the trap depth, or I don't remember the precise number now, but they're not in their ground state. Let's say it's not a Bose-Einstein condensate; it's a thermal gas. And so the extent to which you care about the temperature is if it is that to the extent that sort of motion might couple to the spin degrees of freedom. So for us, it more or less the couplings are kind of, I would say, so there's presumably some kind of averaging over the motion in terms of any axial motion in terms of the coupling that we see. I would say kind of motion could be a decoherence mechanism, but it's not kind of a dominant effect for us. Yeah.
Okay.
And it can also gives rise to a slightly reduced average coupling compared to kind of the cooperativity you would get if every atom were sitting sort of still at the point of maximum coupling.
Got it.
Yeah.
Okay, so there's some more questions here, but maybe let's, in the interest of time, keep going and then we can recycle them for later.
Yeah. Okay. Sure.
Cool.
Great. So, right. So we want to start getting into the graph of getting into control of the graph of interactions. And specifically, ideally you might want kind of arbitrary control over the graph of the couplings. That is a direction that is not out of the question, but to start with, we'll be a little bit more modest and say, can we even just control the dependence of couplings on distance? And if we could do that in an arbitrary way, I would already be quite happy, and this gives us a lot of flexibility. So that will be our goal, is sort of arbitrary control over the dependence of some coupling J on the distance R between two atoms, and which essentially means the distance between array sites. So in order to do that, we need to make position in the cavity matter. And the way that we do that is actually to apply a magnetic field gradient across the system. So we're going to turn off kind of the long-range coupling as a starting point by applying a magnetic field gradient, and then our goal is going to be to controllably turn back on long-range couplings that we want. So first we apply a magnetic field gradient, and why does that turn off the long-range coupling? Well, our physics was that we have these spin exchange interactions. And now if the Zeeman splitting is different at different points in the cloud, then that process of creating a +1, -1 pair only conserves energy if the +1 and -1 atom are sitting on the same site. And if they're further apart, there's an energy cost to creating a pair. So that shows up when we measure correlations in our system. If we measure, for example, after turning on the light for some period of time, we measure correlations between the number of +1 atoms on site I and the number of -1 atoms on site J. We'll see that these correlations are strong on the diagonal, meaning pair creation is happening on individual sites, and weak anywhere sort of off the diagonal. Okay, so that means we can constrain these pairs to form only locally, but the nice thing is we can also now controllably turn on interactions at a particular distance by turning on two laser frequencies in our control field. So the idea is we can now have the possibility of absorbing a photon of one energy and emitting a photon of another energy, and thereby bridging the cost of creating a +1, -1 pair at a particular distance. And this is, so the neat thing is just by controlling the spectrum of our laser field, we can control the distance at which interactions are on. And that shows up in correlations appearing off the diagonal, in this particular case at a distance of 10 sites, that's specified by this difference between drive frequencies. Okay. So the picture is kind of, so that having these more than one frequency component corresponds to having some modulation, actually, of the intensity is the way to do this, an intensity modulation of the drive field at a particular frequency that's going to dictate the distance at which interactions are on. And we can see if we actually vary the modulation frequency and measure correlations versus distance. So each row here shows correlations as a function of distance. Vertically, we're varying the modulation frequency, and you can see that the distance where the correlations are strong actually tracks the modulation frequency. The control is quite precise, so you can really, in kind of discrete jumps, specify our interactions on a distance of 9 sites or 10 sites or 11 sites just by controlling that frequency. So this is nice, and this then generalizes to the point where it's actually easy to use an arbitrary waveform generator to control the waveform of the light. And so that should give us arbitrary control actually of interactions versus distance. So before I get into sort of fancier graphs of interactions, let me give you kind of another picture that I find useful for thinking about this type of control. So I kind of argued that the spectrum of the drive field dictates the couplings as a function of distance, right? If I have a particular modulation frequency, so there's some characteristic frequency at which I would modulate to generate nearest neighbor interactions. If I modulate at 3 times that frequency, I'll get third neighbor interactions and so forth. But I can kind of take the Fourier transform of this picture and actually say, in the same way that the frequency spectrum dictates couplings versus distance, actually the waveform as a function of time dictates the energy as a function of momentum. And so that also turns out to be kind of a nice picture for thinking about this system, is that by controlling the modulation waveform, I can actually control the dispersion relation for spin excitations in this system. And in these equations here, this comes back kind of to a question that was asked earlier, I'm thinking of this big F as representing the total sort of collective spin on site I, that's the sum of the spins of the individual atoms, or equivalently, I can Fourier transform that and write down some spin wave operator that represents kind of spin waves of a given momentum k, and the energy of those spin waves as a function of momentum is given by my modulation waveform versus time. Okay, so one thing that this momentum space picture actually gives us, it turns out that the spin waves of minimum energy, so the minima of the dispersion relation, actually correspond to kind of the momenta at which we have the strongest instability to creating these correlated atom pairs. So in particular, the peaks of the laser intensity correspond to the minima of this spin wave dispersion relation, and those are the momenta where we expect to see strong pair creation. So let me kind of illustrate that. As an example, if we take this case where we modulate at a frequency that gives us interactions at a distance of 3 sites, as a function of time, you'll see kind of correlations show up at a distance of 3 sites and over time kind of spreading to 6 and 9 sites. But if we can also Fourier transform this. What I'm actually measuring here are correlations in the x basis, and if I take the Fourier transform, I'll get sort of a structure factor for this spin texture. I'll see a peak at a particular momentum that corresponds to this pattern of correlations being strong at multiples of 3 sites. And that actually directly maps, that corresponds to a peak in the intensity of my waveform versus time. So this is sort of another nice way of thinking about how we can structure the graph of interactions, or equivalently the dispersion relation for the spin excitations. One thing that this picture kind of led us to realize is that actually I have a finite size system, and so this dispersion relation is actually only defined at discrete points in momentum space. So if you sort of take this literally, you realize maybe I shouldn't be having like a continuous waveform with which I modulate my laser field. Maybe I should actually turn on the laser at specific discrete times. And it turns out if you do that, you do precisely engineer the dispersion relation for actually a finite size system with periodic boundary conditions. So it turns out if we go from continuously modulating the field to actually pulsing on the field at discrete times, we would go from the situation where we essentially go from having a linear chain to a ring in the interaction graph. Or if, for example, if I take this row where there were second neighbor interactions for the continuous modulation waveform, this discrete pulsed modulation waveform gives me interactions at a distance of 2 sites, but also the length of the chain minus 2 sites. So this is a very general technique for actually going from the physical system that we have in the lab to something with periodic boundary conditions. And it kind of highlights the fact that the graph of interactions doesn't need to be the same as the physical geometry. So one of the ways we can kind of check this, I can tell you that based on this correlation plot, we've made something that is not a chain but a ring. But we can also really, in a black box way directly from our experimental data, check what is the interaction graph that we've made. And so the idea here is, we turn on some particular drive waveform, in this case the one that we think should give us a ring-like graph. We have some set of measured correlations, and we ask the question, for these measured correlations, suppose that there's some correct sort of geometry to think about this interaction graph, like this ring. We're going to sort of say, then what I should have is that in that kind of effective geometry, correlations should decay as a function of some notion of distance. It turns out for our system, the natural form of decay is a Gaussian decay. So we say, let's assume that there's some kind of effective coordinates of my sites in some space. What is the best fit set of coordinates to explain the correlations that we measure? And so just from these data, it's essentially kind of a least squares fitting procedure to find what are the coordinates that best explain the correlations. And it in fact corresponds to these sites being on approximately a ring. So we can get the coordinates, and the other thing we can do is actually ask how strong are the couplings between the sites. And in this picture I've drawn here, these bonds are also extracted directly from experimental data. So for the system of n sites, there are sort of roughly n squared bonds you could imagine drawing. And actually every possible bond is drawn in here, but the opacity of the bond represents the strength of the coupling that's inferred from this correlation matrix. and the color represents the sign. So is it a ferromagnetic or an anti-ferromagnetic interaction? In this case, it was all ferromagnetic. And what really pops out is the ring, right? So the other bonds are there, they're just very faint and you don't see them. So that kind of verifies in a black box way that we've made the coupling graph that we think we wanted to make. And now we can extend that to a couple of other examples. So for example, I could start with, let's take this example we looked at before. If I have interactions at a distance of 3 sites, from these measured correlations, I can infer a geometry. I'll pause for a moment so you can think what geometry will pop out if I do this reconstruction. And what I get in this case is basically 3 individual chains. And this makes sense because I could equivalently have drawn this graph as 0, 3, 6, 9, 12, and so forth, 1, 4, 7, and so forth. Those are kind of 3 decoupled chains. So that is kind of making sense, and now we can try and get a little bit fancier. So here's an example where we said, let's have nearest neighbor interactions with periodic boundary conditions, but let's also add some bonds across this ring. So in this chain of 18 sites, we also have 9th neighbor interactions. That's just some additional modulation frequency we add. We can also control the signs of the interactions. If we change the phase of the modulation by pi, that flips the sign of the interaction. So in this case, we said, let's do ferromagnetic nearest neighbor interactions and anti-ferromagnetic 9th neighbor interactions, measure correlations in this system. And we can, again, do our black box reconstruction technique. And in this case, what actually pops out is a Möbius strip. So, why is it a Möbius strip? It kind of makes sense that, so this red single edge of the strip corresponds to going once around this ring. And these bonds across the wheel are actually these kind of bonds across the strip here. So in fairness, we actually, the order of events was that I asked my students, can you find a way to make a Möbius strip? And, and they did. It wasn't a surprise that this came out. But it was actually a bit of a surprise that just straight from the data, this reconstruction really gave the strip. Okay, and one way you can think about also the fact that we have kind of these different signs of interactions gives rise to these different colored bonds in the reconstruction. And you can interpret that as sort of the spin, the orientation in the xy plane kind of winding once as you go once around the edge of the strip so that nearest neighbors are almost aligned, but opposite neighbors are almost anti-aligned. And now we can play games and send in different modulation waveforms and get out different graphs. So you can have the Möbius strip with the twist, or you can have some kind of a cylinder with no twist. We can have interactions that change sign, or interactions that are all anti-ferromagnetic. Here's an anti-ferromagnetic ladder. Different types of geometries just by changing the waveform of the drive field. Now, one thing that might be a little bit surprising in this system is actually, why is it that the spin correlations, right, these bonds indicate the sign of the correlation, the color of the bond, why is it that they match the sign of the coupling? It's actually not obvious, because what I've done, I haven't just sort of adiabatically prepared a particular state here. I've suddenly turned on the light, just suddenly turned on interactions. And it's not at all obvious that I should prepare something that looks like a low temperature state of this system. So it turns out the reason why that happens, or one way that I like to think about it, is that when it turns out in this our rubidium atoms, we have actually, in addition to the linear Zeeman splitting, there's a quadratic Zeeman energy, which means that the energy of a +1 - 1 pair is actually a little bit higher than the energy of 2 m=0 atoms. So that means that when we create these pairs, we actually can lower the interaction energy by increasing the quadratic Zeeman energy, and that allows us to make things that sort of look like low temperature states of this XY interaction Hamiltonian. So just as an example, when we program in this anti-ferromagnetic ladder, this is kind of a simple example of a frustrated interaction graph. Ideally, all of the spins on each triangle would anti-align. They can't quite do that. The best they can do is find some kind of 120-degree-ish order, roughly 120-degree angles. And when we measure the spin correlations in this system, they match onto that. So nearest neighbors are almost anti-aligned, but if I take like sites 0 and 3, they're almost aligned. The spin correlations show that, and when you Fourier transform them, you can see 2 peaks spaced by 2 pi over 3 that match that 120-degree order. Okay. So that's kind of an indication that this system is finding something that looks like a low temperature state of the XY model. And actually, for generic non-local models, that's actually an NP-hard problem. Not for this case of the triangular ladder. You could have guessed the answer, right? But at least in this simple test case, it finds something that looks like a low temperature state. And now we would love to explore kind of, can you use this same physics to for more complex graphs, perhaps disordered graphs, which there are various ways to add disorder, to still find low temperature states, and is there a way that the system, these quantum dynamics, can give some kind of an advantage? And that's an open question that we would love to explore experimentally. I'll just briefly comment that one thing we've also been thinking about on the theoretical side is, are there cases where one can kind of have a known way of getting a quantum speedup for certain optimization problems? And it turns out for that partition problem, number partitioning problem I mentioned at the outset of my talk, we have a theoretical proposal for using a kind of central spin type model to where the sort of weights of objects map to couplings of individual spins to a central spin, to actually apply a known quantum algorithm, namely Grover's search algorithm, to obtain a speed up for solving this problem. So if you want to read about that, you can look at this paper here. Okay. So, but coming back to what I've shown you so far, we've been able to use these programmable interactions to realize some rather exotic geometries, to realize frustration. We can have interactions that change sign as a function of distance. That's a feature of models of, for example, spin glasses, which could be an interesting direction to explore. One can even go beyond controlling the sign of the interactions to controlling phases, which could be interesting for studying some topological physics. Some of these things can also be studied in other platforms. So this ladder geometry you could realize also with local interactions. So we'd really love to do things where the non-local interactions play a role. And I will get to that next. But before I can I pause for a question?
Yeah, sure. Yeah, that
great.
sounds good. So first is just a quick clarification. If you could just repeat what the axes of the best geometry reconstruction plots are.
Yes. I guess we can use this as an example.
Yeah.
Yes, okay. So essentially, the axes are coordinates in some kind of imagined space. So the idea is we would like to find a set of coordinates where the interactions look somewhat local. And we're going to pick, in this case, we choose what dimensionality we assume. So like we assume that we're working in 3 dimensions. And we're going to try to find some coordinates that here I've called r sub I, that, so I is a label of a site in our physical array of atoms. But we're going to try to find a set of coordinates such that correlations decay as a function of distance in this new effective geometry. So this is kind of a way of saying what is the best geometrical representation of the interaction graph we've generated. And it's essentially a least squares type minimization to find these coordinates from the measured correlations. So measured correlations give us a notion of effective distance, and we use that and we say, can we find a set of coordinates that match those effective distances? So the axes here are x, y, and z, the coordinates in 3 dimensions.
Okay. And maybe I'll ask just 2 related questions to this point, and then I'll save the remaining questions to the end. Another question is, can you describe all the timescales involved in setting these couplings? For example, how many periods of the modulated couplings are needed to establish the correlations, and what sets the timing for the on-off modulation?
Yeah, I think the on-off modulation, that's referring to this pulsing that we do.
That's my understanding of the question.
Yeah. So typically, okay, so there's a characteristic time scale that we actually think of as the Bloch oscillation period. So if you had a tilted optical lattice, there would be some period of Bloch oscillations. In our case, it's a sort of the magnetic field gradient is a tilted potential for the spin excitations. And there's a characteristic time scale to get a 2 pi phase between adjacent sites due to the magnetic field gradient. So that we call the Bloch period, and typically we go for at least, for something in the range of, let's say, 2 to 6 Bloch periods. So in this example where I showed correlations versus distance, correlation spreading over time is actually measured in units of Bloch periods. And the effective Hamiltonian I've written down, this sort of distance-dependent interaction, strictly speaking, is true kind of stroboscopically at integer multiples of the Bloch period. So I think that was part of the question. How long do we go? Anywhere from 2 to 6 block periods. What was the second part?
Um, if you could, I mean, that mostly answers the question, actually, I would say.
Okay. Mm-hmm.
And then one related point too, and this is actually from me. So for inferring the coupling matrix from the correlations, this is sort of in a time independent picture. Like if I had an atom tunneling on a lattice, right, I might find correlations between sites that are distant, even though there's only a nearest
Yes.
for tunneling.
Great.
So
Yeah.
so like how do I sort of
Yeah.
what goes into this kind of inversion?
Yeah, so this is a great question. So yeah, and I showed you we can see the correlations spread. So why does it not look, if they've spread, like there are interactions between those sites? So what we actually do is we take this correlation matrix and we invert it, and it turns out that the inverse of the correlation matrix gives us an inferred coupling. And so the way that this works is it turns out actually even if you have correlations spreading, so you have some correlated fluctuations in the magnetization on certain sites because correlations have spread. If you take this inverse correlation matrix, it takes out any sort of variance that's already explained. So for any pair of sites, it basically is, we're basically taking out anything that's already explained by correlations between other sites, if that makes sense. Sorry,
I see. So
but yeah.
does that mean like if I make one of these correlation plots at a time ti and then also at a time tj, I could do the exact. It'll be the same. Okay, cool.
And I'm not sure how carefully we've verified that, but there are kind of two ways of thinking about this. One is sort of more a statistical way of like, what are the correlations that are not, once I've taken out anything that's explained by other sites, what are what is essentially the coupling I need between these sites to explain those correlations. That's one way to think about it, and the other one is basically if you assume that you have, if you ask actually what are the correlations in a thermal state at low temperature of an XY model, it turns out that the inverse of that correlation matrix is the couplings in that XY model. So there's kind of two different ways of getting at this idea that the inverse correlation matrix is the correct thing to use.
I see. And the latter one would be sort of an equilibrium picture where sort of by construction you're time independent.
Yes, yeah. And of course there's an assumption that what this does is generate something that looks like a low temperature state of the XY model, and there's a reason to think that from our model for the dynamics.
Cool.
And then there's just a purely statistical argument as well.
Yeah.
Yeah.
Cool. Thanks. So yeah, let's keep going, and then I'll ask some more here.
Okay. Cool. Okay. So let's get to an example of something where really kind of you couldn't do this with just local interactions. The non-local interactions really give us some kind of unique capability. So for that, we drew inspiration. So we asked the question, can we build a sort of a toy model for some ideas from quantum gravity? So what do I even mean by that? Kind of the idea that you might be able to use some quantum system that you build in the lab to explore anything about related to quantum gravity comes about from the conjecture of holographic duality. So this is a conjecture that for certain strongly interacting quantum systems, there's an equivalent description in terms of a classical field theory with one additional spatial dimension. So here I've kind of sketched some 2D interacting quantum system, and the concept is that if you try to come up with some effective low energy description of the system by going through a process of renormalizing the degrees of freedom, so some kind of coarse graining process, that process of renormalization gives rise to effectively an extra dimension. And in certain cases, and in that additional dimension, there's potentially some curvature of this space that captures something about the structure of correlations in the quantum system. And so somehow we need this extra dimension to account for entanglement. So that's the concept. And when I heard about that, I kind of wondered, well, is this, I love having ways of visualizing quantum states. I showed some pictures before of things like squeeze states, but when you get to more complex many-body states, could something like this holographic duality be useful as a way of being able to visualize and understand many-body quantum systems? And on the flip side, there's sort of a very deep question of, is it possible that gravity itself actually is something, and so space-time curvature and gravity fundamentally actually arise from entanglement among some microscopic degrees of freedom. So that second one is not something I feel equipped to answer in the lab, but we can at least ask, can we sort of explore this concept in experiments with quantum systems that we build? So in order to do that, I benefited immensely from getting to collaborate with theorists with a deeper understanding than my own of these ideas of quantum gravity. And in particular, my collaborator, Steve Gubser, had been thinking very deeply about the question of kind of what is the mathematical description behind the reality which we experience as smooth space-time, but which in all likelihood is discrete at a fundamental level because of the existence of the Planck length as kind of a fundamental shortest length scale. So Steve actually formulated a version of this holographic duality where the role of this sort of emergent extra dimension, this kind of so-called bulk geometry, is played by a tree graph. And you can think of the tree as a discretized version of a curved space. Why can you do that? Because in the example I've shown here on the left, kind of the circumference of the system, if we take that to be n, the radius of the system is only log of n, right? And that relationship would not hold in a flat space. That requires some negative curvature. So this is kind of a discretized model of a hyperbolic space. And so if we think of this as a model for this idea of holographic duality, the mapping would be that the physical system of n sites corresponds to the leaves of the tree. And this curved space, the so-called bulk geometry, is the rest of the tree graph, so these interior vertices. Okay, and actually some of these tree-like systems, there have been examples of realizing tree-like geometries in the lab, like this nice paper from Andrew Hauck's group where they used superconducting circuits to directly realize kind of a tree structure. In our case, we're not going to try to build the tree itself. We would like to see the tree structure emerge as the correct description of quantum correlations in a physical system. So what's a toy? But we had some idea of a toy model that might allow us to see that. And so the toy model is that you have a system where spins or sites in our array talk to any other site that's separated from it by a distance that's a power of 2. So distances of 1 site, 2 sites, 4 sites, 8 sites, and so forth. And we'll add one ingredient, which is a power law exponent that we call S. If S is less than 0, interactions decay versus distance. So they're on at these discrete distances, and they decay versus distance. And that then is not too different from a linear spin chain. So the strongest interactions are between nearest neighbors. Or if S is greater than 0, then interactions, sorry, let me say that one more time. If S is greater than 0, then interactions actually grow with physical distance. So the strongest bonds in this ring that I've shown here are across the ring, right, between sort of furthest neighbors. And in that case, maybe this just isn't the right way of thinking of the graph. I could rearrange it so that things that are strongly coupled are a bit closer to each other. And the conjecture is that the right way to think about this is having some effective geometry that's this tree graph. Okay, so let's just see. So we can easily build this, and we're going to kind of check whether that actually emerges as the right description of our system. So, right, we can easily build this by just programming in the right modulation frequencies into our drive field. And they're sort of at multiples of powers of 2 multiples of the Bloch frequency. And so when we do that, we can measure some correlations versus distance that, as a function of really like physical distance in our chain, have some kind of weird non-monotonic behavior. They're strong, for example, at distances of 2 sites, 4 sites, 8 sites, kind of makes sense from the couplings we program. And then if the right way to think about this system is as the sites being leaves on a tree graph, if we sort of reorganize this correlation plot so that the sites are arranged according to the positions on the tree, then maybe these correlations will start to have sort of a simpler looking structure. So it turns out to get to the position on the tree, you need to take the site number and reverse the order of the bits, and that gives you a mapping from physical position to position on the tree. And when you do that map, then the correlation plot starts to have kind of a block structure, right? So you can see, maybe you can see a block of 8 here, you can certainly see some blocks of 4, blocks of 2, and that kind of matches the hierarchical structure of the tree. And if you plot correlations as a function of the correct measure of distance on the tree, which is related to how many levels you need to go up and back down to connect two sites, then they decay smoothly as a function of distance. So that started to kind of suggest that the tree is a good description of this system. But what I really wanted to see is, can we actually, in the same way that we, say, reconstructed the Möbius strip, can we reconstruct the tree graph directly from our experimental data? And that is not quite, it's not immediately obvious how to do that, because unlike in the case of the Möbius strip, where every vertex is a physical site, in the tree graph, only the leaves of the tree are physical, and everything else is supposed to be this emergent geometry that describes something about the correlations in the system. So what we do is we start by sort of doing our usual reconstruction procedure, where we look for what is the kind of best fit arrangement of the sites, in this case in a two-dimensional space, to explain the correlations we measure. And I'm showing this here for the case where interactions shrink versus distance. That's not too different from a spin chain, to the case, and also the case where they grow versus distance, which we think might give us the tree. So that's our starting point, but then we actually kind of try to do this coarse graining procedure that was supposed to give us this emergent extra dimension. So what do? We draw bonds between the pairs of sites that have the strongest correlation. And if we do that for the kind of situation where nearest neighbor interactions dominate, we just connect the nearest neighbor sites. On the tree graph, we get something like this, and now we treat every pair of connected sites as a new larger site and look again where are the strongest correlations and draw new bonds. And as we repeat that procedure, we build up actually precisely the tree. So this comes directly from the experimental data. So this is a kind of illustration of this idea of an emergent bulk geometry, in this case represented by the tree graph, which again is kind of a discrete model for a curved space, which is starting to kind of get at this idea of seeing this idea of holographic duality in an experiment. One sort of last thing I'll add to this is that we can also kind of tune smoothly between the two limits of the thing that's like a nearest neighbor chain, where interactions shrink versus physical distance, to the tree-like geometry, just by tuning this power law exponent. And there are kind of one thing we can do is measure, as a function of this exponent s, how strongly correlated two different halves of the system are. And we can choose actually how we cut the system into two halves. So if we cut it according to the physical geometry, those are the blue points here, then when s is less than 0, like for the sort of case where interactions shrink with distance, the two halves are relatively weakly correlated. For the opposite limit, the tree-like case, we have to actually cut according to the tree, and these are the green points here, for the two halves to be weakly correlated. And if you sort of go in between, the two halves are strongly correlated both for the cut along the physical geometry and for the cut along the tree. And in fact, no matter how you cut the system, so the purple is showing, consider all possible ways of cutting the system in half, how strongly correlated are the two halves. And there's a peak at this point, s equals 0, where interactions are kind of flat versus distance and at all of these power of two distances. So here kind of everything is strongly connected to everything else. And we believe that this is actually potentially an ideal condition for seeing that phenomenon of fast scrambling, where information can spread exponentially quickly from one to kind of all sites and quickly become hidden in entanglement. So that's kind of the something that we've, in simple cases, analyzed theoretically, but it would be wonderful to be able to actually simulate this phenomenon in an experiment. Okay. So I'll just kind of wrap up by saying I've shown you a high degree of control over the graph of interactions. We can control the sign of the interactions, ferromagnetic, anti-ferromagnetic. I focused on things we can do with flip-flop interactions, but another knob that we have in our experiment, it turns out, is to control, do we have flip-flop interactions or Ising interactions? And that's something we've used actually to show that these flip-flop interactions compared with Ising interactions can actually help to protect the coherence of the collective spin in situations where one has all-to-all interactions. That potentially has some applications to creating metrologically useful entangled states and protecting coherence in that context. And I'll just lastly say, if all of these exotic non-local interactions are too much for you, we do also work with local interactions in our lab, and have been doing some experiments using off-resonant coupling to Rydberg states to realize a transverse field Ising model, and are exploring applications of that to spin squeezing, and perhaps optimally controlling squeezing using some ideas that our moderator has proposed. Okay, so with that, I will just remind you again that we have shown, in addition to kind of control of the interactions, the possibility of using the interactions as a natural way of kind of generating effective low temperature states of an XY model that could have some applications in optimization. And we've shown this kind of reconstruction of effective geometries from experimental data that perhaps could also be useful in some other contexts. This idea of also reconstructing even this emergent bulk geometry, I think it would be fascinating to explore whether there are other cases, perhaps in quantum critical systems, where that same type of emergent bulk geometry can be seen in other quantum simulation contexts. We would love to sort of expand the types of programmable graphs we realize, also perhaps exploring topological physics by controlling the phases of the couplings. And then we're really interested in asking kind of what types of multi-mode entangled states can we generate that might have applications ranging from kind of quantum enhanced sensing or imaging to graph states with applications to computation. And then ultimately, everything I've shown is using these kind of large ensembles, but an interesting and important future direction would be, can one also go towards a regime of even stronger atom-like coupling and single spins per site, which would perhaps map more cleanly onto some models that are of theoretical interest. So I will just, with that, kind of thank the team that has worked on these experiments, and particularly Eric Cooper, Avakar Parawal, and Philip Kunkel were the key people involved in the measurements I showed today. And I've also highlighted some earlier contributors in red, as well as our collaborators.
Great, that was a fantastic talk, Monika. So we're a bit over time, but that was well used over time. Maybe I'll just ask one or two questions here, and then remind everyone that we have this post-Vamos discussion time, and that Zoom link is in the chat already. So just one clarification question. So for the recovering the tree-like structure from the correlations, when you say that you use a sort of a set of nodes and look at the correlation between like two sets of nodes, or two sets of leaves, maybe is the right terminology. Does that mean that you're basically just like adding the two spin vectors at those two sites? Like, what does it mean actually to look when you say, yeah, so like when you look at the correlation of 1,9 with 5,13 to get like the next part of the tree, what does that mean mathematically in practice?
Yeah, so it literally means we have some total spin on a given site, and then once we've decided to draw a bond between 1 and 9, we add those up and just think of them as a larger spin.
Got it. Okay.
And I will say, I think for us it was like maybe a little bit surprising that very basic process works. It's sort of, ideally you would be looking at something like entanglement entropy, right? And that's not easy for us to measure. But even just this sort of very natural experimental observable turns out to already give this tree structure.
Cool. And then maybe one other question here that sort of touches on a couple of the questions that have come up. So this notion of preparing a low energy state or low temperature state from the sort of resulting dynamics in the system. Are there ways that you might imagine preparing ground states? Because, for instance, being able to prepare a ground state of a system with periodic boundary conditions would be a super unique capability for an AMO system. But I also, like right off the bat, for instance, to know immediately how you would do that. So are there ideas about that?
So I think that so first of all, if you're really trying to prepare the exact ground state of the quantum system, I think so. You know, that's perhaps most interesting in this regime of a single spin per site. But you could also ask, I think, even in the regime we're in with these ensembles, can you kind of be more adiabatic, for example? And so first, maybe I should start by emphasizing that the way I think of what we're doing now is that the correlations that we observe match the correlations you would expect in a thermal state of a at some low temperature of a classical XY model. And in some sense, the temperature is actually going down as a function of time. But right, so it's preparing a low temperature state of a classical spin model. And that's interesting already because those classical spin models are, there are these hard optimization problems that map to classical spin models. But now I think your question is, can we start to prepare ground states of the quantum Hamiltonian? And there, I would be inclined to think we should take a more adiabatic approach. And so one thing you could do, for example, is we have ways of tuning the quadratic Zeeman shift. So you can use like an off-resonant microwave field, and we do this sometimes to tune the quadratic Zeeman shift. And so you could start from a case where the ground state is all atoms in m equals 0, and adiabatically tune to a regime where the ground state has population in +1, -1. And so through some combination of adiabatically tuning the quadratic Zeeman shift and also the interactions, that would give a way to come closer to actually preparing the quantum ground state. And that type of approach has been applied in the single mode case in a Bose-Einstein condensate to prepare twin Fock states, actually. And so we would love to kind of generalize that to these multi-mode systems where we can control the graph of interactions.
Cool.
Yeah.
Okay, so maybe to close here, Monika, can you give me access to the sharing so I can just quickly share the slide?
Yes, let me do that.
Cool.
So I will, how do I?
Think you're good. Okay. All right, so just to announce, so next week we'll have, or sorry, 2 weeks from now, we're no longer a weekly schedule. We'll have Bryce Gadway from UIUC. He'll be presenting on his work in Hamiltonian engineering and synthetic dimensions, same time as usual. And then the quantum science seminar didn't have anything up yet, but definitely check their website if you want to stay in the loop on things from there. So with that, let me remind you to go to the post-VAMO Zoom discussion, and thank you again, Monika.
Thank you so much.